Hi, dear students. Good morning to one and all. Dear students, in the last lecture, we discussed about the aromatic hydrocarbons, which is the second topic in the unit number 3 in the second semester of Fybsc. Dear students, already we have completed most of the topic of this aromatic hydrocarbons, and we are going to discuss now the remaining part of this aromatic hydrocarbon. Dear friends, if you remember about this aromatic hydrocarbon, then we particularly discuss the condition for the aromatic hydrocarbons or the aromatic compound, which is given by the Huckel's rule, that any compound which is cyclic, planar, having conjugation and containing 4n plus 2 pi electron is known as the aromatic compound. Dear friends, in the last part, we also discussed about the various types of aromatic compound like benzenoid, non-benzenoid, and the heteroaromatic compound. Dear friends, today in this part of the video, we are going to talk about the another type of the compound which are less stable than the aromatic compound, and these are not able to obey or satisfy the condition given by the Huckel's rule, but these are the cyclic containing 4n pi electron, and these are also having conjugation and the planar structure. These compounds are called as the anti-aromatic compounds. So today, dear friends, in this part we are going to talk about some chemical properties of aromatic compound as well as what is meant by anti-aromatic compound. So dear friends, today we will discuss about the concept of anti-aromatic compound. Definitely this compound is quite different whenever compared with the aromatic compound. Here there are some compounds which are cyclic, planar, having conjugation, but these are less stable than the corresponding acyclic unsaturated compounds like alkenes, and these compounds are called like the anti-aromatic compound. That's why here, based upon this, we are able to define this anti-aromatic compound as cyclic unsaturated compounds having planar structures and containing 4n plus 2 pi electron, and they do not obey the Huckel's rule, then these compounds are called like the anti-aromatic compound. So here anti-aromatic compound is defined as the phenomenon by which the cyclic conjugated compound is destabilized by a closed loop of pi electron. Here this is one compound here which is called as cyclobutadiene. Definitely in this it is cyclic, it is also planar, it is also having conjugation, but it contains 4 pi electron. That's why this compound is called as the anti-aromatic compound. So here another examples of this anti-aromatic compound is the cyclopropene anion, that is anion of this, and it is also cyclic planar having conjugation, but it contains 4 pi electron, means 4n pi electron. So another example of anti-aromatic compound is cyclooctatetraene, and another one is that the same structures can be drawn here. It is non-planar structure, but here already we discussed about the aromatic compound. These are more stable. Anti-aromatic compounds are less stable, and whenever you will talk about non-aromatic compounds, they show the stability equal to the corresponding open chain compound having same number of pi electrons. So dear friends, in this way, if you look at some chemical properties of this aromatic compound, then the aromatic compounds are electron rich compounds, so these are the nucleophilic in nature, and that's why the characteristic reaction of aromatic compound is a electrophilic substitution reaction. So remember that aromatic compound always readily react with the electrophile, and this shows the aromatic electrophilic substitution reaction, and which is the characteristic reaction of aromatic compound. So for example, suppose we will talk about the benzene. Benzene contains circular pi electron cloud above and below the plane of the ring, and these are loosely attached pi electron can be donated, and hence benzene behave as a nucleophile in nature. Therefore it gives electrophilic substitution reaction like nitration, substitution, halogenation reaction. And there are some common steps in this electrophilic substitution reactions shown by amines of aromatic compound like benzene. The first one is the attack of electrophile. In this case, benzene or the aromatic compound reacts with the electrophile and it gives the formation of sigma complex. After this sigma complex loses the proton, that we call it as loss of proton, and the state is called as aromatization. Here, the intermediate carbocation ion loses its proton in presence of an base which is formed in the same reaction, and definitely so the and this is and in this step the aromatic character of the ring is achieved, and this is the first step of the reaction, while the earlier one was attack of electrophile, it was the slow step of the reaction. So here I can show you the first step attack of electrophile. Here the electron cloud, pi electron cloud of benzene attacks this electrophile and it gives the formation of benzenonium ion, which is the carbocation that can be stabilized by the resonance effect of this benzene ring. And in the next step that we call it loss of proton, which is also called as the aromatization. So base present in the reaction mixture accept attack this proton, and in this way there is a aromatization is achieved in this reaction, in which one of the hydrogen of benzene is replaced by means of an electrophile. So dear friends, if you look at these two steps, the attack of electrophile is responsible for the disappearance of this aromatic character. So in this step aromatic character is lost, and this is the slow step of the reaction, while in the loss of proton the aromatic character of the benzene is achieved, and hence it is a fast step of the reaction. So here if you look at the energy profile diagram, then this is the first step which is the slow step, and it is the next another step is the fast step. This is so in this way we are getting two intermediates, and this is the benzenonium ion which has less energy as compared to the transition state first and the transition state second. So this is energy profile diagram. So dear friends, in this way we can discuss some examples of electrophilic substitution reaction. The first one is the nitration. Actually nitration is the introduction of nitro group in aromatic ring, in which one of the hydrogen of benzene ring is replaced by means of a nitro group. So it is carried out by refluxing benzene with nitrated mixture, that is concentrated HNO3 and concentrated sulfuric acid is called as nitrated mixture at 60 degrees Celsius. So general reaction is benzene reacts with the nitric acid in presence of concentrated sulfuric acid, then the one of the hydrogen of benzene is replaced by means of nitro group, and that's why the product is called as nitrobenzene, along with the formation of water, which is the byproduct in the reaction. So nitration cannot be carried out by using the only concentrated HNO3, as the reaction is slow. The nitration can easily take place with fumed nitric acid at room temperature also. So the reaction takes place in the following steps. As the first is the formation of electrophile, means nitronium ion. So in which what happens? Sulfuric acid reacts with the nitric acid, and there is a protonation of this OH group, and in this way we are getting the formation of nitronium ion with the formation of base HSO4 bisulfate ion. So this nitronium ion which behave as electrophile, here in the next step this nitronium is attacked by means of this benzene, and it gives the formation of pi electron, and it gives the formation of sigma complex. Then what happens? See, so in this is the nitro group, here this is the benzene, so yeah, it will attack this nitro group. Definitely the formation of carbocation take place. This carbocation is stabilized by means of a resonance effect of this benzene ring, and it gives this hybrid. In the next step, the base HSO4 minus ion, which is already present in the reaction, will attack this acidic proton, and this is so that the aromatic character of this benzene is achieved in the next step. So this is the two-step reaction, in which the first step is the redetermining step. If you look at the first step, this is the first step in which both benzene as well as nitro group take part. That's why this is second order electrophilic substitution reaction. So there are some advantages of using the nitrogen mixture is that during the nitration, water is produced as a byproduct, and hence the concentrated H2SO4 is used, which is dehydrating agent and absorb the water, hence the rate of reaction is increased. So here H2SO4 works as the dehydrating agent in this reaction. H2SO4 is again stronger acid than nitric acid, and hence it can protonate nitric acid very easily and help into generating nitronium ion, which is the electrophile in this reaction, and hence the nitration of benzene is carried out by the mixture of concentrated nitric acid and sulfuric acid. Another example of electrophilic substitution reaction is called as sulfonation reaction, in which one of the hydrogen of benzene ring is replaced by means of an sulfonic acid group in presence of concentrated H2SO4 or sulfur trioxide, that is oleum, at 40 degrees Celsius or 25 minutes of temperature. So in this case, the first step is the formation of electrophile, in which the two molecules of sulfuric acid undergoes, that is protonation, and gives the formation of SO3. So in the next step, attack of electrophile. So this pi electron cloud of benzene attack this sulfur trioxide, which is the electrophile, and definitely it gives the formation of carbocation, that we call it as the benzeneonium ion, and it is the slow step of the reaction in which the aromatic character of benzene is lost. In the next step, this base, which is already present in the reaction, it will attack this acidic proton, and the aromatic character of this benzene is achieved in this step, and this is the first step of the reaction. Finally, benzene sulfonate ion gets protonated in presence of water, and it gives the benzene sulfonic acid. So this is the product here. So another reaction is known as the halogenation. So here the two molecules of halogens in presence of Lewis acid like APCl3 gives the formation of electrophile, that halogen cation, that is chlorine plus. So this halogen, which behaves electrophile in presence of this benzene pi electron cloud of this benzene ring forms a sigma bond with this electrophile, and it gives the formation of benzeneonium ion, and in which the aromatic character of benzene is lost again. So that's why it is the slow step of the reaction, because stable compound get converted into unstable. In the next step, this non-aromatic compound benzeneonium ion gets its aromatic character by the loss of proton in presence of base, that is APCl4 minus, to give the substituted product, that we call it the halobenzene, or if it is chlorine, then it will be called as the chlorobenzene. So here in this way we are also able to get the bromobenzene, only we have to change the halogen. So this is a very simple reaction. And another one is the Friedel-Crafts alkylation reaction, in which one of the hydrogen of benzene ring is replaced by means of an alkyl group in place of anhydrous AlCl3, which behave as the Lewis acid and alkyl chloride or the methyl chloride. In this case also, in presence of Lewis acid, initially alkyl chloride reacts with the Lewis acid, it gives the formation of alkyl cation, which behave as electrophile. In the next step, attack of electrophile, in which the pi electron of benzene ring attack this electrophile, and it gives the formation of benzeneonium ion in presence of Lewis acid, and this is the non-aromatic compound. So again, it is the slow step. So in the next step, the aromatic character is achieved in the step known as the aromatization, that we call it the loss of proton. So base AlCl4 minus attack this acidic proton, and the aromatic character of this compound or the benzene is achieved, and the product is alkyl benzene. So in this way we are also able to form another compound, that is acyl benzene. The reaction is called as the Friedel-Crafts acylation reaction, in which only difference is that benzene in presence of acetyl chloride and Lewis acid AlCl3 gives the acetophenol with the formation of HCl as a byproduct. This mechanism is similar to Friedel-Crafts alkylation, and in this reaction acylium ion is electrophile instead of alkyl carbocation. So here in this case, this acyl chloride reacts with the Lewis acid HCl3, and it gives the formation of electrophile acyl cation. So this acylium ion, which is the electrophile, reacts with the benzene and it forms the sigma bond with this benzene and it gives the formation of benzenonium ion, which is stabilized by means of an resonance effect of this benzene, and in which the aromatic character is lost, and this is again the slow step of the reaction. In the next step, which is the first step of the reaction, the base in the reaction mixture attack this proton, and that's why it gives the aromatic character to the product known as the, that is ketone. Particularly it is, if it is what is the R, that will decide the name of this compound, but here this AlCl3 behave as a catalyst in this reaction. So another, this same reaction can be carried out in presence of acetic anhydride also, the product will be same acetophenol. So here, dear friends, in this way we have completed the discussion of anti-aromatic compound as well as some chemical properties of the chemical reactions of aromatic compound with the help of example of benzene. Dear friends, in the next part of the video we would like to discuss about the electrophilic substitution reaction of monosubstituted aromatic compound like a benzene. So we will discuss in the next part of the video about the chemical reactions of monosubstituted aromatic compound with the help of again benzene. So thank you very much.